Right, we are now going to be looking at two more of our parent functions, the cube and cube root functions. So our cube parent function is x to the third power. And just like our other parent functions, we can have various transformations with these. You know, our horizontal vertical shifts, horizontal vertical stretches, reflections over x or y axis. And so that would change the way our function looks. We're also going to be looking at our cube root function, which is the third root of x. That's our parent function. And again, we have the same types of transformations in our cube root function. And what makes the cube and cube root function a little bit different from other ones we've looked at prior, such as quadratics, when we had a parabola, h and k represented the coordinates, the location of our vertex. But in a cube and cube root function, we don't have a vertex, we have what's called a point of inflection. And so hk represents the coordinates of that point on our graph. So just like we did with our square root function, we are going to look at what these parent functions look like and describe their characteristics. So what we're going to do is complete the table and plot the points. And so for our x to the third power, our x cubed function, there are no restrictions on what x can be. And as long as I'm inputting whole numbers, I'm going to get whole numbers as an output. So what we have here is 0 as kind of our middle, and then a couple negative and a couple positive values so that we can get 5 distinct points. And if I cube negative 2, that's going to be negative 8. If I cube negative 1, that's negative 1. 0 to the third power is 0. 1 cubed is 1, and 2 cubed is 8. So here are my 5 points that I'm going to plot. And this one's going to go a little bit off the graph, but that's okay. Okay, and there we go. There is our cube x to the third power function. Let's talk about the characteristics. My point of inflection is at the origin 0, 0. My domain is all real numbers. I have no restrictions on my domain, so you can say negative infinity to positive infinity or all real numbers. My range, again, is also all real numbers. And then my x and y intercept are both at the origin, 0, 0, for our parent function. Okay. Now I'm going to be looking at my cube root function. And this one, again, when I was looking at inputs for my square root function, I wanted to do perfect squares so that my output would be whole numbers that are easy to graph. Well, I want to take the same consideration with my cube root function and input perfect cubes in order to get an output that's a whole number that's easy to graph. So what they have done here for us already is picked some negative perfect cubes and some positive perfect cubes. So the cube root of negative 8 is negative 2. The cube root of negative 1 is negative 1. Cube root of 0 is 0. Cube root of 1 is 1, and the cube root of 8 is positive 2. So here are now my 5 distinct points that I'm going to graph. And connect them with my smooth line. And then I can fill in my characteristics table again at the bottom for my cube root function. Again, my point of inflection is at 0, 0. My domain is still all real numbers. My range is all real numbers, and my x and y intercepts are both at the origin. So keeping this information in mind, this knowledge we have now of the graph of our parent functions for both cube and cube root, let's look at some transformations. So what I'm going to do at the top is fill in. These are the same tables that we had when we graphed our parent functions. So I'm going to go ahead and fill these in. And these are going to be our reference points when we are plotting our transformations, just like we did with the square root function. So here we are going to identify whether the function is a cube or cube root and describe the transformations applied. Then we're going to graph with 5 distinct points. Well, that would be ideal. However, the graphs on this page are a little small, so we are going to be doing 3 distinct points. If we had a bigger graph, 5 is definitely reasonable, but there's just not room on these graphs on the page. So let's jump into it. Starting with A, this is a cube function. And I can see that I have 3 transformations taking place, so I'm going to go ahead and list those out. It looks like I have a shift to the right 1. I have a vertical stretch by 2. And I'm going down 1. So just like we did last time with our square root functions, what I'm going to do is take these points, my distinct points from my parent function, and individually do these 3 transformations to all of them to plot my transformed graph. Now, the ones that I'm going to be able to fit are these middle 3. When I have stretches with the 8s, that's going to end up being at like 16 and negative 16, and there's just not room for that on my graph. So these are the 3 I'm going to do for my cube functions. So starting at 0, 0, that's just a nice starting place. I'm going to go to the right 1, and then a vertical stretch by 2. My y-coordinate is 0. 0 times 2 is still 0, so that one's not going to change it. And then I'm going down 1. So there's my first transformed point. Next, I'm going to go ahead and do 1, 1, and I'm going to go right 1, vertical stretch by 2, and down 1. Then at negative 1, negative 1, I'm going to go to the right 1, vertical stretch by 2, and down 1. And then I'm going to connect the dots to make it look like the same shape of my parent function. And there is my first transformed cube function. Let's look at B. This one's also a cube function, and it looks like I, again, have 3 transformations. So this time I'm going to the left 3. I have another vertical stretch by 2. And I'm going up 4. So let's start with those same 3 points. I'm going to go at 0, 0 to the left 3, 1, 2, 3. Vertical stretch is not going to affect it, and then I'm going to go up 4, 1, 2, 3, 4. Okay, then 1, 1, I'm going to go to the left 3, 1, 2, 3, vertical stretch by 2, and then up 4, 1, 2, 3, 4. Lastly, negative 1, negative 1, I'm going to go to the left 3, 1, 2, 3, vertical stretch by 2, and up 4. Connect the dots to make my curve, and there is our next transformed function. And now we are moving on to our last 2, and these are both cube root functions. So what we're going to be transforming are the middle 3 from this table from our parent function of the cube root. So let's look at C. I have 2 transformations here. I am going to be going to the left 6, and I'm going to be going up 5. So starting at 0, 0, I'm going to go left 6 and up 5. Then at 1, 1, I'm going to go to the left 6 and up 5. Negative 1, negative 1, left 6 and up 5. And so as I can see, it'd be really nice if I could fit more on this table, but that's just not going to be possible. So here are my 3 points, and I want to connect them with a smooth curve that looks like my cube root parent function. And there is C. Okay, and then last one, I have another cube function, and I can see 2 transformations here. One is a shift to the right 4, and the other one is a vertical shrink by 1/2. So starting at 0, 0, I'm going to go to the right 4, and my y-coordinate is 0. 0 times 1/2 is 0, so that one is staying there. 1, 1, I'm going to be going to the right 4, then the vertical shrink by 1/2 takes my y-coordinate of 1 and halves it. So I'm just going to eyeball where that half is. Then negative 1, negative 1. Again, I'm going to go to the right 4. 1, 2, 3, 4. Shrink by 1/2. And then I'm going to connect the dots to look like my cube root function. Okay, so that is some more information on the parent functions for our cube and cube root, as well as some transformations of those 2 functions.